So 21, I can't make the text any bigger on this window, but 21 this really goes to understanding how angle relates to arc length. Okay, really goes to understanding how angle relates to arc length. So what do we need? We need so what are we trying to maximize or minimize? So we want what kind of function? We want volume. And what is it going to be dependent on? Theta, right? So this is going to be, if we can get this function, then we know what to do from there, right? So probably the whole ball of wax here is getting this volume function. Okay, so let's just in general, what's the volume of a cone? So you can look that up. And in general, volume is 1/3 pi r squared h. So what do we need? We need the radius, and that's a constant, right? So that's easy. Oh, wait a sec. No. Sorry. Yeah, no. It's not constant, right? So we need the radius. We need the radius as theta, and then we need the height as theta. Both of those as theta. Is that right? Okay. So how are we going to do that? What's that? S equals theta radius. And S is what? So this right here, she wants to call that S. Okay? And she said that arc length, if theta is what? Theta is radians, then what does its number mean? It means number of radius lengths, right? Number of radius lengths. So in centimeters, how many centimeters is that many radius lengths? How many centimeters is theta radius lengths? 20 times theta, that's right. Because 20 is the length of one radius, and we have that many radius lengths. So that S will be 20 theta. Okay, so why does that help us? What's that?
You said you need to have them as theta, so you can divide by 20 and S over 20 equals theta. So then you have theta equals something, so you can plug it into your volume equation.
Okay. So how does this S relate to our finished cup? So we're going to get this R from the circumference of the final top of the cup. So circumference is equals 2 pi r. And so what's the circumference? What's the final circumference of the cup once we fold this thing up?
Minus S.
What?
Minus S.
What minus S?
Well, 2 pi r minus S.
Yeah, so it's going to be this circumference, which we know, which is 2 pi times 20, minus S, is going to be the circumference of the top of the cup. Is that right? You see that? Okay, so this circumference of the plate, call it P, is 2 pi times 20. So the circumference of the cup, the cone, is going to be that 40 pi minus S. And what's S? 20 theta. And from that we can, so that is the circumference of the cone, and we can back solve for r by dividing by 2 pi. So r is going to be that thing, the circumference of the cone, all over 2 pi. So we got our r, now we just need our h. So there's our r.
2 theta or 20 theta?
Nope, 20, oh sorry, thanks. Thank you. Okay, am we good now? Yeah, as soon as I make a mistake, shout it out. That's good. Okay, so this is our r, and it can go there. So all we have left is h. How are we going to get h? From here to here.
Well, isn't it Pythagorean theorem?
Okay, right, because so this is, right there, that's our 20, right? This angled edge is the old radius of the disk. You see that? And we know this is r, which we just found. And then right there is height. So 20 squared equals r squared plus h squared. And so h squared equals 20 squared minus r squared. So that looks a little ugly, so we could take the r and put it there, and then take the square root of that thing. But that's looking a little ugly. Is there a cleaner way to get h? Anyone come up with a different way to get h?
Cosine theta, sine theta?
So how does theta, you're talking about this theta? How does this theta work with this triangle? Right? So is that, yeah, I mean you could call an angle like this theta, but we need relating it to this angle theta. So is there a relationship between this angle and this triangle after we fold this thing up in 3 dimensions? Any ideas? Well, I've done this problem before, and I don't remember it being this ugly, because we're going to square this, and then we got to tweak the square root of that whole thing, and that's going to be just that term of the volume equation, and that's feeling awfully ugly algebraically. So rather than Pythagorean theorem, I think there's some kind of reasoning we can use to get this h more directly from theta. But it's not coming to me this time. What's that?
You should just take it off the homework.
Take it off the homework. Okay. If you've got a thought, don't hesitate to toss it out. Anybody got a thought? So what happens when we cut? What else does this height relate to? 20.
Is there somehow you could use the surface area of both of them instead of the surface area equal of each other? I don't know if h is an easy to extract variable.
Okay, that's a good idea. So we could We could take the area of that circle minus that pi piece, and that would be equal to the surface area of the lateral side of the cone.
Yeah.
Mm-hmm.
That's just
Yeah, that's possible. I'm just wondering, is there any way we can take this angle theta and get it to relate to this final product here of the cone? Something to do with the circumference. Okay, well, we'll leave it at that. So, and if I come up with something, I'll let you know. But how about what we did? Does it make sense what we did? This is totally, everything we've done is fine and can work. Just working with that volume equation is going to be a little ugly. But anyway, we got the R, and we used the R to get the H, and so then we'd have everything in terms of theta. So the square root of this whole thing would be our H. But I'm pretty sure there's some better way to think about it. Okay, any questions about that? All right, what's the other one? Last one? 56A. So we got a 3-foot and a 4-foot corridor like this. Okay, and so it says, what's the longest pole that can be carried horizontally around a corner with a 3-foot corridor and a 4-foot corridor meet at right angles? So is this a scenario here? And so what kind of problem is this? Like, what are we trying to do in this problem? Okay, so are we trying to maximize the length of the pole? Is that what we're trying to do? How long of a pole could we get just down this 3-foot corridor here? How long? Infinite length, right? And how long of a pole could we get down this corridor? Infinite length. We're trying to maximize the length of the pole? Around the corner. So what is the constraint around the corner? So for instance, oh, I don't like you. Okay, so what's our constraint? So if I suppose this is kind of the critical spot here. What if I look at this? Is this a longer pole or a shorter pole? So this is the same size as this. No, it's much longer, right? And then what if I, going around a little bit further, what about this? Is that longer or shorter than this, say, this critical point? What are we trying to do here? Is this a maximum problem or a minimum problem? See, what's constrained, we're not trying to maximize the length of the pole. We can have as long of a pole as we want. Okay? But there's some place as we're going around the corner where there is a minimum available distance that we can get that pole around. So this is we're really minimizing the room or the length, allowable room or length. Does that make sense? So this is really a minimum. So we're looking at all these scenarios of how long of a pole could fit, right, at different angles. And so the longest pole we can get is the one that, how do you explain this? The longest pole that you can get is the one that can fit through the, the minimum distance that we have. You see? How often is it doing that? All the time now? I don't think that's my end. Okay. So we're looking at all these different situations. The maximum pole that we can have is the one that will still fit when we have the minimum distance. That's what we're trying to say. Okay, so we'll call that function L. What is L going to be a function of? So we're looking at all these different kind of ways that we can get a pole around the corner. So really, the way to go here is theta. So we're going to name this angle here, say this angle right here, that's theta. And we're saying which angle gives us the minimum amount of length, and that's the longest pole that we could get around the corner. Does it make sense? Okay, so how long is the, oh, so we don't know. All right, so basically we're going to use our angles, and we're going to set up some triangles here like this. Okay? All right, and so then this right here is our angle theta. Okay, and so then also this is theta. Is it okay?
So those are the same angles, correct?
They're the same because these are parallel lines. So that has to be the same angle as that. Okay, so the whole length is, say, L, and let's break it up into L1 from there to there, and L2 from there to there. Okay, so what is L1 in terms of theta, and what is L2 in terms of theta? Well, we've got this dimension right here. What dimension is this? That's our 3, and this one's 4. Okay, so we have a relationship between L1, theta, and 3. What relationship is that? That's our sine, right? This is a vertical height. So sine of theta equals 3? 3 over L1. Okay, and this one we got L2, and we got 4, and we got theta. What's our relationship there? That's cosine. Cosine theta equals 4 over L2. So L1 is 3 over sine. L2 is 4 over cosine. All right, stop me if I lose you. Did I lose you? What was our goal? Our goal was to get this total length right here in terms of whatever angle we're at. Whatever angle the pole is at when it touches the corner. All right, what's this 3 the sine theta the same as? That's 3 cosecant theta. We're actually going to get to use our mastery rules here so we got it. So the length of the pole as a function of theta is 3 cosecant plus 4 secant. Okay, anybody have a question? Did I lose you? Okay, and what do we want to do with this length? We're trying to find what about this length? The minimum, right? The minimum length is like our constraining point, and that's the longest pole we'll be able to have to be able to make it around. Okay, so to get minimum, we're going to take first derivative. Okay, so Mastery. Derivative of 3 cosecant theta. Did we learn anything? Negative cosecant theta. Cotangent theta. And secant theta? Secant theta. Tangent theta. What we're going to do with that? Set equal to 0. So we can attempt to do this algebraically. By switching, we could switch all these back to sines and cosines. So we could switch these all back to sines and cosines and see if that offers a possibility of solving it. So this would be cosine over sine squared. So negative 3. I'm just going to abbreviate cosine as C and sine as S. Is it okay? So this is negative 3. This is cosine over sine. This is 1 over sine, so sine squared. Plus 4. And this would be sine over cosine squared. Equals 0. So we can move that over and then cross multiply. So basically, if I add this to both sides, it's positive, they're equal. Cross multiply, I get 3 cosine cubed equals 4 sine cubed. Okay, we can do it. Alright, and then if we group these back together again, so if group the thetas, we'll get 3/4. We're going to divide by 4, and we're going to divide by cosine cubed. Sine cubed over cosine cubed. What is sine cubed over cosine cubed? Tangent cubed. Now we're home free. So I got tangent cubed equals 3/4. So we want the cube root of 3/4 and then the inverse tangent of that. So what did I say? Tangent cubed equals 3/4. So first we want the cube root. That will give us tangent theta. And then we want the inverse tangent of the cube root of 3/4. Okay, did I lose you? I'll pause for a moment here. Did I lose you? Anybody have a question? What's that? Cotangent. I divided by cosine cubed and then divided by 4. So I got 3/4 equals sine cubed over cosine cubed. Who asked that? Who said should it be cotangent?
I went the other way and divided by.
So if you had 4/3 equals cotangent cubed? Yep, same thing. Yeah. Okay, so what is this? We want the arctan of 3.75 to the 1/3. I got 0.738. What does it mean? So what does 0.738 mean in this context? Okay, so first of all, it's an angle measure. What angle measure is it? Well, okay, so it's the angle measure corresponding to, it's the one critical point of this L theta function. So do we know that it's a minimum? No, we suspect that it is, but because of the scenario, because of what's going on here, we know that if you, yeah, so if we increase theta a little bit, will L get longer or shorter? And if we decrease L a little bit from this, it's got to be longer. So this has got to be a minimum. We can just reason that from the picture. If we want, we could take the second derivative, but we don't want to. Or we could, what else could we do? We could plug in into this. We could plug in an angle slightly smaller and slightly greater. When we plug in an angle slightly smaller, what do we expect for L prime? Positive or negative? If we're thinking that this gives a minimum length, and we plug in a slightly smaller angle, then what about the first derivative? We're thinking this should be negative. And if we plug in an angle slightly greater, then minimum would be consistent with that being greater than zero, positive, greater than 0. Okay? And so then what is the maximum length pole we can take? Well, it corresponds to the minimum length that's available. So what is our, here's our length function. So to find it, we could do 3 over sine of 0.738. Why am I doing this? I have a graphing calculator. So we can do 3 divided by sine of 0.7375, let's say, plus 4 divided by so 9.8, was it in feet? Yeah, in feet. Does it feel about right? I mean, given the setup here, the 3-foot hallway, 4 feet hallway, does that seem like it's ballpark? That it could maybe get almost a 10-foot pole around that corner. Yeah, that's reasonable. Yeah, I mean, if we came out to an answer of 4 feet, we would know that was wrong. If we got like 50 feet, we would know that's wrong. But that seems reasonable. Okay. Did I lose you? If I lost you, please ask a question. Does that make sense? Okay, so any of the others that you didn't get your questions asked or answered, please come find us. Or send, if it's a quick question, send an email. But get your questions answered, okay? They're all important questions. And as you see, setting up the original function, that's the whole name of the game. Because after that, it's all the same, right? You take the derivative, set it equal to 0, and then you verify that you got the max or min that you need, and then you kind of analyze the situation. But it's getting, with all these different geometric situations, it's getting this original function set up that that poses the greatest challenge often. Yes, sir?
Do you think you could maybe go over 21 against next class if you figure it out?
Yeah, I will. Yeah, I'll let you know about that, finding that h in terms of theta. Yeah, that's the key to that. I definitely will mention that. Okay. Any other questions? Okay. Where are we at? Okay, so here's a scenario. The left shows the rate of change The left-hand graph shows the rate of change of elevation, and that's in feet per 100 feet. So this is in foot of elevation per 100 feet, 100 horizontal feet. Okay, so that's the rate of change for every 100 horizontal feet. How many feet does the elevation change? That's the rate. And then this is miles from the border. Over here. So, I want you to write, so starting at, say, from point 8, to, say, 2.1. And here, I'm showing a delta x of 0.4. So I want you to write two expressions. So using the pink, approximating, so the gray here is the actual rate of change function. The pink is the approximating. So using the pink approximating function, I want you to write the accumulated feet of elevation from 0.8 miles from the border to 2.1 miles from the border. Okay? So, what did I just say? I said find, so express the accumulated height in feet on the highway from 0.8 miles to 2.1 miles from the border. Okay? And then in two ways. Express it in two ways. Okay? So this is kind of review from the end of class Friday. Express the accumulated height in feet along the highway from 0.8 miles to 2.1 miles from the border. Go. So express that in two ways. Okay, if you're stuck, talk to somebody. If you've got something, compare it with somebody. Let's move some here. Okay, does that help?
not with my money this time. Second one, there you go. This is going from 1.8 to 2.8. RT, Yes. Rate. Yeah, R story times delta. Fourth rate.
Okay, let's see what we came up with.
Sixth rate.
How about Lauren? Did you get it?
I just did R sub 3 times 0.4
Okay.
plus R sub 4 times 0.4
Okay.
plus R sub 5 times 0.4
Okay.
plus R sub 6.
Times 0.4?
Oh,
What?
wait, just kidding, just R sub 6, right?
So R6. So you want to just add the rate? I mean, what are you doing here? You got the rate times what?
Times delta x.
Times how much of that rate we have, right? How long or how many miles we continue that rate. So what do you want to do here? It's just the rate times the distance in miles that we're applying that rate. So what would you do for this one?
There's only one that stops at 2.1.
Okay. So how long in miles do we apply this rate? 0.1. Yeah. Right, remember we said there's that part of the accumulation where we got to go through the full intervals, and then sometimes we have a partial interval, right? We have a partial interval at the end, and that's the case here. Okay, and then we could also write that as, oh no, say using this one over here. If we call this we can call this the elevation function. Use the e function. How would you use the e function to calculate this? Yeah, it'd be the total accumulated elevation up till 2.1, which would be that y value. Minus elevation at 0.8. Okay, and then we said if where's delta x? There it is. Suppose we make delta x really, really small because we want a much more accurate result here. So I'm going to turn off the... Okay, so that purple graph is still a step function. But our delta x is so small now that it's virtually the same as the actual rate of change function. How can we express it now? So as delta x gets sufficiently small, Corey, what integral?
Starting at 0.8 to 2.1.
0.8, 2.1.
Rx dx.
Okay, and it still equals okay. And so then what about starting at any value, say c, and accumulating to any value? So c is a fixed starting point. We're gonna but x is allowed to vary, and we want a function that gives us the accumulated height starting at c miles from the border until x miles from the border. What's the accumulated height? So can we write a expression for that? Somebody new? Andrew.
Integral from C to X.
Okay.
Rx dx, or sorry, RT dt.
RT dt. And that's going to equal?
E of X minus E of C.
Okay, now here's a key point. What's the relationship between the e function and the r function? So there's this e function and r function. How are those related? So talk to the person next to you. What's the e function? What's the r function? What's the relationship between them? Have a conversation. Go. Okay, how about this Andrew in the back? What's the relationship between those two functions, e and r?
The derivative of E is R.
He's saying the derivative of e would be r. Do you agree with that? Why? So what kind of function is e and what kind of function is r, such that r is the derivative of e?
E is an accumulation function
Yeah?
of the elevation.
Okay.
And then R is the rate of change of elevation.
Agree with what he said? It's perfect. It's exactly right. So well said. So e is the accumulation of elevation from the border. R is the rate at which it's accumulating. Okay, good. Okay, so this is significant. We're about to see why this is significant here. So let's. Oh, there it is. It's hiding. Where are you? It's somewhere here, but it's not. Oh, maybe I did that. No. Where is it? I'm just going to keep going here. Yep. No, but that's actually is this? I can't move it. There it is. Okay, sorry. All right, so here this is this result we just had. So what's the point of this? So take this accumulation function. So what is the rate of change for this accumulation function? Autumn. Agree with that? 2x. Okay? So if this is a rate of change function, so let's tell me, what is this? So what did I just do here? What is that? Yeah, Autumn. The 3 is the lower limit and x is the upper limit. Right. Right, okay. So this is is it open or closed form? Open or closed form? This is what we spent the first first month of the class doing? This is the open form of the accumulation. From 3 to x when the rate is, so when the rate is okay, well now we just talked about, how can we rewrite this? So we can rewrite this how? So, right? F of, try again. Almost. No. It's going to be we want the final accumulation minus the initial, right? Isn't that what we just said in the example? Okay, so why is this significant? So, and then what is that? So what is f of x? What is it? What is f of x? And what is it? What is f of x? It's x squared. And what's f of 3? 9. So this is also an accumulation function. Open form or closed form? Closed form. Same accumulation function, but now in closed form. So this is the kind of the last piece of the puzzle that we didn't have. We had at the whole beginning of the course, we were able to get the open form accumulation from rate. But now that we know how to get closed form rate from accumulation, we also know how to get closed form accumulation from rate. Okay? So this is the open form accumulation for this rate. When do we know it's closed form accumulation? When do we know it in closed form? Well, when we know the accumulation function from which we got that rate. You see? So if we know the accumulation function that gave us that rate, then we can have a closed form for the accumulation function for that rate. Does it make sense? All right, we'll continue this on Wednesday. If you want your quiz from Friday, I can give that to you. You come up.
You were out there in 5 minutes. She's probably just getting up.
Thank you.
You're welcome. Don't. That's not a good way to do it. I'm going to call her Sharon, Christina Trin, Josh, Dan, Tyler. Here, right here, stop, sorry. Corey, Eric, DJ, Corey, yell out if I say your name. Sue, DJ, Tenrui, Adonijah, Lee, Daniel, Richard, Pam? You right?
Yeah.
Pam, is that right? What's your... Pam. Anyone else want their quiz? Anybody else want their quiz?